你觉得他们中国内地很大的好几年没看到这些段。哎，对了，那你是哪个理工学大一点？这边我拿手。
这个是断点，这个是断点，我算的电压。你那个应该是loop， 那个应该是 loop current。这个是14，这个的结果是14，这是正4，这是负4，这个是加6。可以啊，这个完全没反应到这儿了，3个到这儿。
Okay, I guess we can get started. So today we're going to start on a new topic, which I think is very interesting and very important, which is on phasors. Okay, so we're going to talk about phasors. And as I told you before, sinusoidal inputs are very important because once you have a sinusoidal input, the output is also sinusoidal to an ordinary differential equation. So phasors are extremely important for analyzing cosinusoidal inputs. And then because of that, you can define impedances. You can define impedances for a highly complex circuit. Apply Kirchhoff's voltage law and Kirchhoff's current law for a highly complex circuit. So let's figure out what a phasor is. And let's review some of the identities that we have in complex number. Say if C is a complex number, and if C has a real part and an imaginary part, okay, then we know how to find the real part of C. The real part of C is obtained by taking C plus its complex conjugate divided by 2. Okay, because if you were to take the complex conjugation of C, it will be A minus JB. A very simple rule for taking conjugation of a highly complex number is to replace plus J with minus J, or minus J with plus J. And that always works. Okay, if you don't believe me, try that. And that always works. So, if you want the real part of a complex number, you just use this formula. You take these two numbers together, add them, the imaginary part will cancel, then you have A. A is 2A. When you add them and you divide by 2, you get real C. Okay? And then, similarly, the imaginary part of C is defined to be C minus C complex conjugate. If you take this minus that, the real part will cancel, and then you have 2jb, and if you divide by 2j, you get the imaginary part of C, which in this case is equal to A, and this part is equal to B. Okay? So, because of this, you can have very simple identity that the real part of an exponential function looking like this, using the Euler's identity. Using the Euler's identity, this is cosine phi plus j sine phi. So if you were to take the real part of this number, you would just have that. Okay, that follows from Euler's identity. But if you were to use the above formula, it will be C plus its complex conjugate, e to the j phi, plus its complex conjugate. What is the complex conjugate of e to the j phi? Negative j phi. So no matter how complex that number is, the simple rule applies, which is that every time you see j, replace it with minus j. And then when you divide by 2, if you, it's real part, and this also gives you a cosine identity. Another way to express cosine of phi, if you were to take the imaginary part of e to the j phi, okay, if you were to take the imaginary part, then from the Euler's identity, this is sine phi, this is equal to sine phi, and then if you were to apply the above formula, it will be e to the j phi minus e to the minus j phi divided by 2j. This is the sine identity, another way of expressing the sine function of phi. Okay? I think this we all know is just revision. Okay? Because of that, you can use these identities to manipulate very many complex numbers. Say for instance, if you have a function which is real, or maybe it could be complex, if you multiply by e to the j omega t, if this is complex numbers, if you have this complex number, a complex number can always be expressed in terms of its amplitude and phase. The complex number can always be expressed as such in the polar form. All of us know this. And if you were to substitute into the above and take the real part of a complex number times e to the j omega t, you will have this being the real part of the magnitude of f e to the j theta plus omega t. I just sum up the exponent after I'm substituting them in. Okay, I will have that. Okay, everybody follows. I just add the two phases together, and then this means that this must be equal to f. If I use the Euler's identity for this, and taking its real part, I must have cosine of omega t plus theta. So when you have a complex number as such, it can be always expressed in terms of a cosinusoidal function, which means that all cosinusoidal functions can be also expressed in the reverse manner. Okay, that is, if I have any function of this nature, which is a general cosinusoidal function, a general cosinusoidal function, it can always be expressed as a real part of a complex number times e to the j omega t, where the complex number has an amplitude and phase. Okay. So this is a very powerful identity that we will have to use and reuse again. And you have to use and reuse this for your homework and your exam. Okay, not this exam, but the next one. Okay? So let's take an example. of this very simple application of this formula, say if you take example 4.1 of the textbook, that if I have a sinusoidal signal or cosinusoidal signal expressed as e to the real plus e to the j pi over 3 times e to the j 2t. What is this? This is very simple. You just add the two exponents when you multiply complex numbers. I hope all of you know that, right? When you substitute this in, multiply the two complex numbers, e to the j omega t times e to the j theta. If I substitute that in, this would be equal to e to the j omega t plus theta. That's how I get this exponent over here. Okay? So when you have something like this, it's better to add up the exponent when you multiply them. Okay? And then if you take the real part, you make use of the Euler's identity. The real part of the exponential function is equal to that. And you also have to realize that the real part of a real number times an exponential function is just the same as taking the real part of the function out and taking the real part of the other one. Okay? So you have to realize that this is in fact, as a precursor to this, that this is in fact equal to that magnitude times the real part of e to the j omega t plus theta. Okay, and by doing that, you get that one in the above. Okay. The real function commutes with the real operator. Any number that is real commutes with this real operator. That's a mathematical way of saying it. The order is not important. You can put it inside or outside this real operator. If you don't believe me, you can try with any number. Any real number times a complex number is the same as the real number times the real part if you were to do this operation on that. So similarly, this real number can be taken outside the real operator and be written as real part of e to the j 2t plus pi over 3. And then if you were to take the real part of this, you get cosine of 2t plus pi over 3. Okay, is this clear? Because there is quite a bit of manipulation of Euler's identity and then using the properties of complex numbers that you have had in one of your homework problems. Okay, is this clear to everybody? Okay, just remember your complex number properties. And a lot of students get confused between polar form and Cartesian form. A complex number has a polar form. A complex number also has a Cartesian form, maybe f plus jg. Okay, this is called a Cartesian form. This is called a polar form. And don't get confused between these two. And you know how to go from a Cartesian form to a polar form, I presume. Okay. Let's revise that a little bit. How do I go from a Cartesian form to a polar form? First, I have to find the magnitude of C, and then I have to find the angle that these two numbers subtend in the complex plane. The magnitude is given by this line. If I have a real line and then an imaginary line for a complex number, say this is the real part of C, this is the imaginary part of C, that complex number can be represented by this point on the complex plane. Okay, maybe I should use dot here. And the magnitude of this complex number is just this line. Okay, that line over there is the magnitude of C. And then this angle is the phase. This is called the phase. And this is the magnitude. Okay? So to find that phase, or the angle theta, you just use the tangent identity that tan theta must be A over B. Hence the phase angle must be arctangent of A over B. Okay, so this is something that you should know. And you should be able to go back and forth very quickly between the polar form and the Cartesian form. Okay? So, if you're good with this, then you can do all the examples in the textbook with no problem. Say if you do example 4.2. I have g of t is equal to 3 cosine of 2t minus pi over 2. Okay? And it is often said that this number, okay, if I have this number, let me say that, let me not say that first. Okay? If I were to write this as a real part of something, what's that something that I need to put in there? It's very easy. It must have the 3. It must have e to the j. And the phase angle must be 2t minus pi over 2. If you were to do this in the reverse order, you get back the above line. Okay? So it's rather simple. It's just that you have to remember Euler's identity and all those things. Okay? And that this number g, I can say that this is the real part of g times e to the j 2t. Okay, e to the j 2t, and g in this case is equal to 3 e to the minus j pi over 2. Okay, so if you know this complex number, it is as if you know everything about g of t. This is also called a phasor of g. Capital G is called a phasor of little g, or the Phasor representation. Okay, this is called a phasor or Phasor representation. So it's a succinct way to replace a complex sinusoidal function. You just replace it with a complex number. And similarly, I can say that if I were to write this as being equal to real part of f times e to the j 2t, okay, then you can see that f has to be equal to 6 e to the j pi over 3. And this is called a phasor form, phasor representation of the cosinusoidal function f of t. Okay? And if I would have called this in equal to f of t, for instance, okay, then this f is the phasor representation of that cosinusoidal function. Okay? So the phasor is just a complex number with the time dependence removed, with e to the j omega t removed from the complex number. And that remaining part is called the phasor, or the phasor rep of that cosinusoidal function. So things are rather simple. Say if you have one that looks like this, example 4.3. B of t is equal to 2 cosine 6t minus pi over 2. What is the phasor form of this cosinusoidal function? What is the phasor rep? Some of you can do it mentally now, right? So B is equal to 2 e to minus j pi over 2. Or if you were to write this in Cartesian form, it's minus 2j. Okay? Because e to the minus j pi over 2 is just negative j. So the phasor form of that above expression is just minus 2j, or the phasor rep, or the phasor. Okay? So very simple. I hope everybody knows how to do this shortcut and do this mentally. Okay. And then one thing you notice is that there's another way to write this thing over here. Cosine of something minus pi over 2 is equal to what? Sine, okay? Sine of 6t. So a sinusoidal function can be obtained from a cosinusoidal function by just putting a minus pi over 2 there. And minus pi over 2, putting a phase of equal to minus pi over 2 is the same as multiplied by minus j. If you have a phasor, and then if you want to convert it into, if you have just a number, a phasor number which is real, say f is equal to 3, then the cosinusoidal function that corresponds to this is 3 cosine omega t, for instance. Okay, if you keep omega arbitrary. But if you multiply this by minus j, then if you were to find its cosinusoidal form of this phasor, it will be 3 sine of omega t, just omega t, because this actually comes from 3 cosine of omega t minus pi over 2. The minus j gives me minus pi over 2. Minus pi over 2 converts this into a sine. So just remember that minus j, or minus 90 degrees phase shift, converts a cosinusoidal function into a sinusoidal function. Okay? And there's something that you can commit to memory too, instead of having to derive it. Every time you have minus j, just convert it into a sine. Okay? And also, always remember that the argument, the input to this cosinusoidal and sinusoidal functions have to be in radians. Okay? Otherwise, if you punch into your calculator, you might get the wrong answer. If you say 30 degrees, you punch 30 into your calculator. 30 degrees has to be converted into its radian form before the calculator can accept it. Maybe these days calculators are very smart. Okay, but during my time, they were not that smart. So if you put in 30 degrees and forgetting to convert your 30 degrees into radians and take the sine of it, you get the wrong answer. So don't do that in your exam. Okay, remember that all degrees have to be converted into radian form. For instance, what is 90 degrees in radian form? Pi over 2, right? So remember to do that when you do your exam. Okay? So let's do more examples. So you can do more examples, like example 4.4. Okay. So what is the phasor form of 5 cosine 5t plus pi over 2? The phasor form, okay, will be 5 e to the j pi over 2. Okay, but e to the j pi over 2 is just equal to j, 5j. Okay, and what is the phasor form of 5 sine of 5t plus pi? Actually, I have pi over 3 in the textbook, actually, but I put pi over 2. That's okay. I just get you the right answer anyhow. So this will be minus 5j e to the j pi over 3. Right? Because it's a sine form, I just have to multiply by minus j and convert that. Okay? And then we do example 4.5. Example 4.5, if I were to have a function that looks like this, I multiply by j, 7e to the j 3t. How would I find is the cosinusoidal form? Okay, to find its cosinusoidal form, I just put the j in the exponent, and if I put j in the exponent, it becomes pi over 2. Just remember that j is equal to e to the j pi over 2. When they multiply together, add the exponents, I get this, and this is just 7 cosine of 3t plus pi over 2. Okay, so plus j and minus j just give those phase differences. And let's show that phases obeys the principle of linear superposition. Okay, that if I have two cosinusoidal functions, okay, let's call this an h of t. If I know that f of t is represented by this function, e to the j omega t, okay, g of t is represented by the real part of another phasor function times e to the j omega t, okay, then it's quite clear that f of t plus g of t is equal to, if I add these two things, it's like adding the real part of two complex numbers. Okay, I wouldn't go into the detail, but I hope you can be convinced that this is just the real part of adding the two complex numbers. Can everybody see that? Adding two real functions, which are the real part of two complex numbers, is the same as adding those two complex numbers and then taking its real part. Everybody gets that? Okay? That is okay, right? I don't have to go through the detail. I don't have to write this in real and imaginary part and add them. Okay? So, what this says is that the phasor form for h, which is the sum of this cosinusoidal function, is just f plus g e to the j omega t. I can factor out the e to the j omega t and say that the phasor form of h, which is capital H, is just the sum of the two phasor forms. This is a principle of linear superposition. Okay? So H is equal to F plus G. Okay? But I can generalize this to something more and say that if I have, say, HT is equal to K1 FT plus K2 GT, then what is capital H? This is slightly different now. Capital H would be equal to that's right, K1F plus K2G. Okay, as simple as that. Here I'm assuming that I have a real function. F is real, G is real, K1 and K2 are real. And if you go through the math again, you get exactly that. It's just a principle of linear superposition. Okay, K1, K2 are real numbers. Okay, this means member of. Okay, a member of the real numbers. And so this is called the principle of linear superposition. Principle of linear superposition. You can always superpose two phasors and so on. And then there is also the principle of derivatives. I can differentiate two phasors, okay? But let me see if I need to go through all the examples in the textbook. Textbook has lots of examples. But maybe I can just go through them. Since it doesn't take very long to go through them anyhow. So if I have I1t is equal to 3 cosine of omega t, or cosine 3t, I2t is equal to 3 or 4 sine of 3t, I3t is equal to I1t plus I2t. Okay, what is the Phasor form for I3? Okay, you can find the Phasor form for this is just 3. The Phasor form for this is what? Negative 4j, okay? Very good. Some of you are getting to be pro at that. Okay? And then the Phasor form for this would be 3 minus 4j. Right? 3 minus 4j. That would be the Phasor form for that. And also remember one very important thing. You can only add phasors if they have the same frequency. If they don't have the same frequency, it makes no sense. All this mathematics here does not make sense if omega is not the same for all of them. This wouldn't have worked if omega are not the same. I wouldn't have been able to pull this out and factor this and then claim that h is just the sum of these two. So you can only add phasors if the frequencies are the same. Okay? Omega are the same. This is very important. Okay, please remember that. Don't go and add phasors that are of different frequencies. They don't make sense. Okay? So these two have to have the same omega. And omega equals to 3 for this case over here. Okay, and I think the textbook converts this to Cartesian form, or to polar form. So if I convert this to polar form, what is the magnitude of this complex number? There's a very famous triangle, right? That if it has sides 3 and side 4, the third side is what? 5. Very good. All of you know that. Okay? And then e to the j theta, and theta is arctangent of 4 over 3, right? Minus 4 over 3. Minus 4 over 3. And do you know what the angle is?
Pi over 3.
Pi over 3? No. I don't think it has a simple answer. Okay. I don't think it has a simple answer. I don't remember what the angle is. Okay, example 4.7. This is example 4.6. Example 4.7. Okay, example 4.7. Then you have v1 of t is equal to sine of 5t. v2 of t is equal to 2 cosine of 5t minus pi over 4. Okay. v3 of t is v1 of t plus v2 of t. What is the Phasor form of v3? Okay. So you can just figure that out, right? So this, actually I have a 3 here in the textbook. Okay, I have a 2. So v3 would be just the sum of this Phasor form, which in this case is, because it is a sign, it's minus sign that you put a minus j, so this is minus 3j. Okay, and this has a 2. Okay, the phase is e to the minus j pi over 4. So you just add the two Phasor forms. Okay, and that is your answer. And then you can convert this to polar form if you want it. If you don't like it into Cartesian form. But what do you have to do before you convert this to polar form? This is in a mixed form. A part of it is in polar form, a part of it is in Cartesian form. So to convert this into polar form, it's a little bit complicated, right? What do you have to do before you can reach there? You convert everything here into Cartesian form first. Okay, you convert this into Cartesian form. Okay, and in Cartesian form, this is 1/√2, or 1 minus j. Okay, you can do that. Euler's identity, you'll get this number. Cosine of pi over 4, sine of pi over 4 is just 1/√2. Okay, and then you multiply by this, you add them all together, you get a Cartesian form. And after you have the Cartesian form, you convert into a polar form. Okay? So those are just details, but something that you have to know how to do, or what to do in an exam, right? If you're faced with this difficulty, and then you get confused how to find this polar form, okay? Now you know what to do, right? So let's look at the derivative principle. Let me see, I still have some time left. So differentiation of phases is very simple. If I have a function that is related to its Phasor form in this manner, if I differentiate this with respect to time, what do I get? If I differentiate with respect to time, I can actually take the derivative inside the real operator. In other words, the differentiation operator and the real operator commute with each other. Okay? If you don't believe me, you can try this in great detail. Write this in Cartesian form and then put the differentiation on the Cartesian form and then see if this really works.